So today we'll be talking about variational methods, which is quite an advanced topic in terms of even deep learning and neural networks. But one of my purposes is kind of to try to show the underlying logic or the unifying principles in statistical methods and models. And specifically, since the variational autoencoder and later the GANs, the generative adversarial methods, and there are other generative methods, of course. Some of them we're skipping, like the restricted Boltzmann machines that kind of started with generative approaches. There are the flow models, but starting with this slide, I want to say that we kind of moving to modeling probabilities and mapping probabilities. So some motivation about why consider a generative problem. So evidently in music, one of the tasks is generative task, right? Evidently. So you would want something that is able to look at data, distribution of data, music, corpus of pieces or recordings, and extract some regularities. Part of this was the representation aspect we spoke last time. And part of this is also how to trigger these representations or how to generate more examples. Very much also the same, setup or state of mind as in the information theory or the coding approach, where you seek a representation, seek encoding that treats actually your data as an information source, as a probability source. And if you encode it efficiently, you arrive at indices, the codes, which cannot be compressed anymore. So they're uniform distribution or Gaussian distribution, depending if you want to put some constraint on the variance there. And again, kind of like same stuff here that requires a little bit more insight. Why Gaussian or uniform are our basic functions. So for this slide, let's assume the uniform is kind of the most intuitive, right? Uniform we cannot compress. I quote Hinton on the bottom, why we would want to have a generative problem, but what it is. So starting from the top, given a set of examples, y drawn from an unknown probability distribution. So this is, if this is statistic, you can say just want to measure the probability to be able to derive the likelihood or sample from this distribution. If this is information theory, you could say you want model information source. So if you have y distributed as P of y, we want to find a mapping y prime or y tag, whatever, of f of x, where f, or so that x is a uniform distribution. And then we basically generate stuff from x, and we'll have a new distribution of this y comma that approximates our P of y. I think we have, with the dice game, with some other examples we have discussed, kind of becomes a little bit more intuitive that we would want to throw a dice and then have some kind of a mapping, some lookup table, some function, maybe a neural network, maybe a graph that you can do a random walk on that graph that will eventually spit out different probabilities or will give us a distribution of the data that has to do something with the real world, and in our case, musical world. And why? So as Inga says, to recognize shapes, first learn to generate images. And canonical example is imagine a pink unicorn. So this is kind of an example of being able to generalize. Ability to generalize is also, of course, important to recognize, because you train on, no matter how big your set of examples is, you want to extract some regularities that will allow you now to judge something that wasn't seen. in your training data. So this ability is the generalization ability. This is why we keep basically training set and validation set. We don't want to overtrain. Really, we want to be able to kind of allow some noise that will introduce more options. So a pink unicorn, nobody has seen a pink unicorn, but you can imagine it because you know it's a unicorn. This one actually looks more like what is it? My Little Pony. Yes, it's a horse and it's pink, but you can kind of do this metaphorical combination of concepts. You can think that this is also a creative act here. So there are a lot of kind of extensions to the idea that if you can generate stuff, you can also be creative. So moving on with this idea, the generative model in variational autoencoder, I'm going to jump right into the variational autoencoder here. It keeps this idea of encoder-decoder that we have seen yesterday. And in our previous lecture, we actually said that, you know, the bottleneck, I mean, the layer that connects P and Q is computed by some sort of gradient descent, or if you want to solve it in a closed form solution as PCA, you can compute the correlation matrices and the eigenvalues, eigenvectors. This is really, we didn't prove anything about the PCA. We kind of shown some motivation. Actually, PCA has a lot of visual intuition, but the math is really more of an algebra. In autoencoder, kind of, I think the architecture is much more evident, and the optimization of the loss function is kind of more straightforward. So if you combine both, you can enjoy maybe a little bit of that intuition of the PCA as a geometrical embedding, and encoding, decoding through a bottleneck, which is the variational, not variation, just the autoencoding aspect. But then, you know, we have to depart a little bit from that concept because, first of all, neural networks, we introduced nonlinearities, and also because today we'll kind of go and look into the problem of probabilistic modeling or mapping, also from the kind of PCA perspective, to kind of keep that connection. But having said all these disclaimers, what is different about variational autoencoder right now, and then maybe about probabilistic versions of PCA later, is that between the encoding and the decoding, there is this kind of a pretty complex looking set of additional blocks where, as you see, they have mu and sigma, and you have a sampling and you have a normal distribution. So everything here that, you know, if you can follow my mouse, is a probability. And this specific diagram is the trick that actually made the variational autoencoder so powerful, that allows us to introduce basically a random element between the encoder, between the encoder here and the decoder here. So we still have a neural network here, we still have a neural network here, basically mapping latent states or mapping data into some kind of latent representation, and this latent representation being decoded into you know, a version of the data. We still have a loss function here, but this whole stochastic layer, if you wish, is a big you know, big challenge. How to add it, how to compute it, and conceptually, basically, what it tells you that the latent state, or whatever this bottleneck is between the encoder and decoder, is actually a probability distribution rather than kind of a geometrical set of points. And specifically, this one is the trick that made the variational autoencoder, the Kingma paper, and that it does this representation of randomness as sum and multiplication. We'll talk about this, and this is called the reparameterization trick, which made this setting possible to be done in a gradient descent. Basically, you could optimize now the whole model end to end by using this specific representation, which is, as I said, the reparameterization trick. So keeping the highlights is that the middle layer is the probability distribution, and the shape of this distribution is found by learning a transformation of the standard normal distribution. So this is what we have here. We have a normal distribution here, this n, distributed with zero mean and unit variance. And we learn these mappings, these matrices, basically these will be neural networks, that once we take a random sample from a normal distribution, we multiply it to scale it to get the right variance. We add something to get the mean, and then we basically transform this set of independent normal variables into a multidimensional Gaussian kind of cloud. But this cloud can have, now clusters in different points with different variances. So this kind of takes a cloud in the middle and spreads it out to other locations. And this is the mapping that we'll be learning, okay? And we'll see some examples later and run some code. So the second part of this lecture, when we talk about generating from MIDI or clustering chords, we'll try actually to visualize these things. The basic elements of generative model is that we have a latent space representation, and the goal of this latent representation is, of course, to reconstruct the training data, but also because it's, in this case, it's kind of a probabilistic, you hope that it will ignore irrelevant deviations. So it will basically, well, I would say that the most intuitive example would be like in the case of data reduction, where you assume that the dimensions that you throw away are noise. So by kind of compressing this or finding more of a compact representation, you'll be able to ignore these irrelevant deviations and throw away noise and keep the structure. Then for our purposes, once we have the latent manifold, you want to be able to sample or even walk the latent manifold in some kind of a maybe continuous way to interpolate between points. So applications like in painting and also musical kind of melodic in painting, which is actually the same word, it's being used from visual domains, or interpolation between musical points. And there are actually applications that do that. You know, if you go on Magenta, and they have some tools that actually you can download either random standalone or you can plug them into software like Ableton Live that allow you to take like 2 chunks of MIDI and be represented in some latent space, and now it will interpolate smoothly. These are fun examples to look at. Maybe we'll show this later. I don't have this right now in the slides. But the whole idea is that if you want to interpolate data, let's say, you probably want to make your trajectory in the latent space rather than on the data itself. So the encoder learns mapping from input to some representation, lower dimensional manifold, and then when you basically move in that manifold, because your mapping captured the structure, then it both ignores the noise orthogonal to the manifold. Actually, these examples started from one way to reduce these methods is to look at denoising autoencoder. We skip that, but just keep it in mind, you know, if somebody goes sometime to kind of look more in depth into all of these approaches. And one way also to introduce variational autoencoder is just to take an denoising autoencoder where you add noise to your data and then try to ignore. And this idea of orthogonal to the manifold is actually just kind of reminded me of an image from one of these papers where you can see actually how what that autoencoder does is actually throws away irrelevant dimensions and sticks to that latent space manifold. And my manifold, you know, the idea is that because it's lower dimensional, it's not a line, it could be some curve, and you can move on that curve, but you can still reduce the dimension. So the underlying principle, and also the term that you might have heard, and it might sound a little kind of mathematically or statistically complex, but I think the idea is simple. And the idea is, as we said, we want to approximate some distribution Px of data x. What variational Bayes does, because the whole setting kind of logically was done in a Bayesian context, but the variational approximation basically, you can call it also variational inference. We're not doing inference, we don't really use Bayes, but since we were using Bayes theorems in the next step, so I put this name here. What you do is, the trick is to approximate P of x with another distribution Q of x. And in some sense, that Gaussian noise that now is being mapped to non-unit variance zero mean Gaussian is still an approximate distribution, okay? And what we try to do is have this trial distribution Q on the latent space Z. So one important part about this slide is really just introduce the notation. We have latent variable Z, and we have a trial distribution Q of Z. And then the Bayesian part comes here by using the conditionals. And so we think, or we assume that there is a latent state, sort of a graphical model, if you wish, if you have heard about graphical models. You assume that you see X in the world, but there is some latent state Z, and that actually is part of that mechanism that generates X. So they have a joint distribution, X and Z have a joint distribution. This is why you have also the posterior distribution or the conditional on Z given X. But this might be too complicated, so we introduce another distribution Q, and we can measure how well P and Q fit or match by using some distance, and we'll be using the KL distance, the Kullback-Leibler distance, the KL distance, which is very close to cross entropy, just has an entropy part in it also. Graphically, you can think that you have this complicated distribution that you don't know how to model, but Q of Z maybe is a Gaussian that you do know how to model. So you will approximate your unknown distribution by shifting that Gaussian from 0 to the right location and spreading it out so it optimally matches PZ of X. So it kind of gives you that motivation that we don't know how to express the true distribution, but we might be able to approximate it well enough with some simple other distribution. So what is the purpose of that latent variable, the Z, in variational Latent Coder? This is kind of the core idea, both of variational Latent Coder and of so-called expectation maximization, idea that we can approximate our distribution or our log of the distribution, sometimes called likelihood or evidence. So if this is called evidence, there is this mathematical trick that just goes all along. So you kind of like realize what this means, and the proof here is pretty easy, so I can walk you through that one. But once you have that, this gives you kind of that basic approach to so-called evidence lower bound trick, the ELBO. Okay, so yeah, here it's the acronym spelled out. So what is evidence lower bound? So part of the approach in statistical modeling now is that we basically want to find the model P of X. So kind of we mentioned already, if we have different candidate models, the one where the data basically gives the maximum probability will be our candidate for choosing that model, right? I mean, this is kind of the logic. If you have a lot of data and you have several candidate models, the model that maximizes the likelihood of the data is probably the one that generated that model. I think it kind of helps to keep this in mind, because we kind of take it for granted that we want to maximize this, but like y. So yes, there is a certain assumption here, a concept that this is kind of the way you would reason about selecting probabilities. Now, going into some mathematics here pretty quickly, if you assume that actually X exists in the world together with Z, so you have joint probability, okay, we could basically average out and get back P of X by marginalizing. Basically, we have an integral that calculates everything. Integral of P of X is Z dz. I don't have this step written out explicitly. But what you can do also, we can then multiply and divide by some other Q Z of X. So this is divided here, but the fact that you have this expectation over Q of Z of X, you can think about this, that this Q Z of X is actually in the integral, and you integrate over Z, okay? So basically we didn't do anything here, the log comes from here. This is basically inequality. Now, but if we do that, then comes this ELBO trick, and if you use a so-called Jensen inequality, you can kind of, because of convexity of the log, you can prove that you can basically now either put the log inside or take the expectations outside. So the log and the expectations switch places here. And the next expression is just, yes, because you put the log inside, you can now convert this ratio into difference of the logs, and you end up with this expression. So I didn't prove this step in detail, but you know, I welcome you to go and kind of just check out where the Jensen inequality comes in, the convexity of the log that actually makes this inequality stand out. So this is the ELBO. This is the evidence lower bound. Why is it useful? Okay, or what is the idea of evidence lower bound? So first of all, if we are able to find Q so that this is maximized, probably will be better off, because that will say that, you know, that will show that we have a good approximation, because this is a lower bound. So we actually want to push this lower bound up by now trying to look for different Qs, because we couldn't do this for the P. P was too complicated, but we can have now maybe some way to optimize the Q and push this up, and hopefully we'll get an equality here, right? So you can also do the math in a slightly different way and show that there is, you know, an equality, not just inequality, that if you take this expression and you add to this the KL distance. KL distance is our P log P divided by Q, or in this case, it will be Q log Q divided by P, because this is the way it's written, Q and P. If you add this, there is actually an equality here. So when will ELBO be exactly like the log of P? When this is 0, right? So max ELBO is going to happen when the Q of Z of X equals exactly P of Z of X. What does that mean? So again, we think now, let's go and look into this graph. We have the data, and now let's give it names. Q becomes the encoder. Of course, this encoding in information theory sense. You know, think about this as a code book, but everything is actually probabilistic. So you encode by sampling from a distribution QZ of X. It takes a while to wrap your mind. This is why really the information theory for me was kind of the right way to approach it, because if you're happy with this way of thinking about information, then this is the encoding. I mean, also all Shannon proofs are done in this way. So this is your encoding, posterior distribution over some other variable given your input. And then once you sample that Z, you now decode it. And again, the decoding is again a random process. You sample now from a different distribution P of X given the input Z. Encoder, decoder, the standard kind of lodging. So of course, that kind of suggests that Z is a compression. You can also think about this as a regularization, and we'll talk about why this is a regularizer, but it kind of many times in machine learning, you don't only provide your loss function, but you also provide some kind of a condition that the function that you're looking for will be smooth, sparse. So this is now a very popular and strong way to kind of enforce, not only kind of the samples will lie on some kind of a nice manifold. In one way to say it, in a different way to say it is that basically it allows you to generalize. It avoids overfitting by kind of putting some kind of a constraint on the type of models you're willing to consider. And then you will not overfit because that overfitting will be too complex of a model. So regularization is really a common process. The canonical simple examples of regularization in regression are that you want to keep the model. Let's say if you fit like a polynomial to a bunch of points, you want to keep lower dimensional. You want a polynomial, maybe not linear, but maybe quadratic, but not too high, because otherwise you can fit like anything to anything. You can have a very wiggly model that will fit every point, and then when you sample a new data point, it will not fit the model because just the model learned the example. So regularization is a general term that also helps understand some of the aspects of what we'll be seeing. Next, it's of course a generative model that's based on formulation, variational approximation, and also because of the way VAE is done, it allows us to do optimization. This is hard to kind of like really appreciate right now, because you could do these things with sampling and other approaches like Monte Carlo that will take you much longer time. So let's move on and talk about latent variables. Okay, so kind of like take a detour or go back to basic concepts of clustering, and then we'll talk a little bit about GMM, because we use concepts like ELBO to understand what, I mean, there's still an underlying question. Why would you want to introduce probability on the latent space, and why PCA or the usual encoder are not enough? Okay, so in order to kind of address this question, and mostly to give an intuition and examples, we're going back to much more simpler model, which is clustering, and then GMM. And I remind you, we mentioned, or we have seen the word Gaussian mixture model when we spoke about HMMs in speech. GMM is a very popular model in modeling the distribution of basically of the observations of speech. So you have the hidden Markov model that switches, the hidden Markov one that switches between the phonemes, but then the realizations, the acoustic factors, or the parameters of your speech model are usually modeled with the GMM. So GMM doesn't have time structure, but it is a clustering structure. But before going to GMM, I want to look into k-means, which is a deterministic version. So by comparing k-means with GMM, I think it will give some intuition about why we want to use variational encoder or randomness in the latent space rather than have a deterministic latent space. So this visualization is about k-means. K-means is a clustering method. I know that it was running, so I think you already kind of got some idea what it tries to do. The idea is that given these data points that didn't have initially any color labels assigned to them, you eventually will separate them into groups, and hopefully, that grouping, that clustering will make sense in the sense that, one color will kind of associate closely related points, right? So how is this k-means process, how it's done? Basically, you have the data. These are the points, and initially they're all kind of just lying out there. We don't know how to cluster them or how to divide them into groups. But we assume there's three groups. So there is an assumption. We assume that you have a certain number of clusters, and then you throw three initial cluster centers. So these are the circle, this big circle, this big plus, and this big whatever the multiplication sign, if you want. So these two crosses, the diagonal cross, the plus, and the zero are initial points that you throw in, and you say, we think that these are the cluster centers. Of course, they're totally wrong, but they already induce a partition on your sample space, and this partition is actually shown as these lines that divide the space between these three cluster centers. So each one has its own kingdom, and these are the boundaries between these kingdoms. Once you have, at each iteration, these three centers, you kind of assign the points to that Voronoi region. These are called what Voronoi regions. Now, after you do that, and you already had an initial coloration of your points and assigning them to, again, to the pluses, the diagonal cross, and the zeros, you can recalculate the mean. So once you have this hard assignment of points, you recalculate the mean. This will move the cluster center to a new location, and you kind of repeat this whole process. So again, this is an iterative process, and we have been looking at this animation for long enough that now maybe let's just take one look into one iteration. So I'll walk you through that, but this is what it does, right? It initializes the center clusters. Let's wait for it to restart. Okay. Okay, it initializes, it divides them, it estimates new centers, that's the moving, and it repeats until it gets stuck. Basically, there is an optimal solution. It depends on the initialization. I mean, it will converge, and not always to the same solution, but once it converges, it is basically at least a locally optimal division of these points into clusters. So now let's generalize this to probabilistic setting. And the difference is that in the previous example, these were hard divisions, hard assignments, hard clustering. You had the boundary and you could be either here or there, right? But if you don't want to put the walls here, we can allow soft assignments, which means that every point, okay, in this new set of data points, actually belongs to some extent to any of these clusters. So even this point, it has the highest likelihood, it has a probability of being here, but I mean, this clustering, this Gaussian, so these are like two-dimensional bell shapes, bell-shaped curves. So this is stall and then kind of basically fades out or tapers out. But I mean, it kind of extends infinitely. So actually there is some probability that this point belongs here. There's probability, of course, that it belongs here, but there's also probability that it belongs here because, I mean, these ripple waves kind of go all the way to here as well. So we assume now that our model is a mixture of Gaussians. Again, you assume that there are a certain number of Gaussians. So in this case, we also have 3 Gaussians. Each Gaussian has some prior probability or weight, okay? Because this is not a hidden Markov model. It's hidden model, but it's not a hidden Markov model. There is no time here. It's just probability of being generated from distribution 1, distribution 2, distribution 3. So it's kind of just that part of the hidden Markov model that generates the observations. So our goal now is actually to estimate these parameters, and our model data is going to estimate, the locations and the variances of each of these Gaussians, and also the mixing coefficients. And here we come to the idea of expectation maximization, which is basically the same trick. We have very much the same idea as ELBO. It's just solved differently. Okay, so what we do, we have this log likelihood. We do the same trick we did before. So actually, this is a good way to go through what I was kind of just explaining by moving the mouse and now I'm kind of have these equations written explicitly. In this case, it's instead of integral, we have only sum because we have n is the number of points. You have this sort of a graphical interpretation. So you have your data, but your latent states, it should be z here actually because it's the z. You kind of sample from some latent space, and then this induces now your probability for generating your data point. So what is this sampling from your latent space? It's basically telling you, let's choose first the cluster, okay, and then sample from the cluster. So the 3 urns model we've seen before, it's exactly that, just that there is no finite state machine that moves between them, okay? So choose your urn and then draw a ball. I mean, the big difference here is that, you know, we don't have also coloration, so don't take this too literally, but there are three different data distributions here, and you first choose the Gaussian. So what you do here is we introduce this approximate or trial distribution Q that you choose a cluster, one of the 3 ones, okay? And then, of course, you have a probability for each point to belong to each one of these clusters. So because we said this is soft assignment, soft clustering, so each point can belong to each one of these clusters. You can average this out, so you can check the math. This is basically just divides. This is 1. So right now, that's exactly that trick. Again, the Jensen inequality that allows us to move it here, and we have again the same expression of ELBO. This L is exactly the ELBO, which is written with a finite set of parameters in the Q, and instead of integrating on all the data points, we sum on the discrete number of data points. And that's the Jensen inequality I was referring to. So expectation maximization actually solves or maximizes ELBO by 2 steps. One is called the E step, one is called the M step. So what are these steps? Well, you can see that what we have now is a function that has 2 parameters. It has the parameters that we want to estimate, and then you have this trial distribution Q, which is actually the current version or the current step. So this will be an iterative process. So every process you will have some sort of assignment of clusters, which is still not correct, but it's kind of the steps like we've seen before in the KL. And for that step, okay, we can basically take and recalculate the parameters of the distribution by argmax. And this way, what we do is basically we can show that in this E step, this is kind of the reassignment of points. We can show, or I mean, the whole idea is that you take and assign the points to the class. So we have the points assigned to the clusters, and now we can calculate, you know, the Bayesian way going backwards, and now calculate the posterior of the cluster centers. Okay, so instead of recalculating the means and averages, well, or in order to recalculate the means and averages, which is done here, you still have to kind of reassign the distributions, the probabilities of these clusters. And this is done by this Bayesian step. So you have this posterior distribution, and by taking this posterior distribution, that's the best update you can do to the distribution of the cluster centers. And once you do that, now you can actually change or update the means and the variances of your distributions. So kind of visually, it can be represented as iterative process. So what we have is given some theta and q, okay, and we have this ELBO, basically lower bound math that shows that we can kind of now look into this function, and this function, these Gaussians are kind of a smooth looking function. This is kind of the true. So the blue one is this intractable probability of your samples given the true family of distributions. So kind of the logic, again, I think just to understand this problem setting, I think is the hardest part. And we assume that the data could have been generated from a family of very complex distributions, and they could be parameterized with theta. So each point here will give you some kind of a probability of seeing the data with a family of all possible true models, but we don't know how to model P. Okay, but ideally we would want to search this space theta and find the highest probability and choose this is our model, right? And we kind of mentioned already this some sort of an assumption that's kind of the Bayesian view of the world. That this is kind of the best interpretation we have to the data by maximizing the likelihood. But still, we also implicitly assume that we can search for this maximum in a family that distribution that is very complicated. Since we cannot do this, we approximate this with some tractable distribution, and we build this Q, and now we have this likelihood function. So at every point, okay, we can actually take the maximal Q, and which will be the posterior distribution over the clusters, and take this as our new model. So if this is the model, we basically take the argument that will give us the likelihood in that in the world of these functions, okay, p of x, and we kind of match this one, and we update our q. Once we updated our q, we now have a new maximum here. This maximum will correspond to true probability here, p of x, with this new set of parameters. We will do one more step, and we'll basically now shift that red function so it matches the same point here. It will give us a new maximum here, and if we proceed with this process, we'll be stuck in a local maxima. Yes, we'll kind of come here and it will not change anymore, but that's the process of expectation maximization. And the main reason kind of to show this for me was, first of all, it's a good chance kind of to go back and talk about some statistical method below, not the shallow methods like GMM, but explain what they are. But in general, it kind of gives this whole setting or understanding of why we want to do this approximator, use the trial distribution. And the EM algorithm written out very differently is used in HMMs as well. But the concept itself is that for the joint distribution, P of X and Z, so again, we introduce latent variables and we have parameters of our model. And we have the data that we observe. So assuming that we have a joint distribution over observed variables and latent variable Z, governed by some parameters theta, the goal is to iteratively maximize the likelihood function with respect to theta, and this is the model we want to find. So the first step, right, we have some set of old parameters, and it allows us to now estimate the posterior of Z. Okay. Again, one point to note here is so Z is probabilistic. That's what allows us to write all these conditional probabilities. Theta is deterministic. This is something that allows us to do differentiation and calculate derivatives. So in this process, we don't really do any derivatives, although we do find argmax here, but you can kind of calculate this analytically. But the logic is the following. We start with some initial model, and we'll keep updating this. So at first step, it's some kind of theta 0 initializing. With this setting and the way we define our model, we can write now the posterior distribution of z given x. Okay, this is the E step. And then once we have this, okay, now we can write this new expression. Okay, we have this posterior distribution. We have this joint model that we defined. Now we can average over all the possible clusters. We get a new function, and now we can update on the other parameter theta. Okay, given that we had an old theta. Okay, so this step we update the parameters. So this is a kind of an iterative procedure that moves between posterior estimates over the latent variable c, which allows us then to calculate a different function and update the parameters. So we kind of can update. In a second, we'll do the same exact process in a neural network. Okay, but we'll do this as a optimization, as a differentiable thing, rather than these discrete steps. Because here it kind of assumes that you could write everything out. You can actually, you have to write these expressions analytically, and then you can write, and then you can have actual algorithms that estimate this, let's say for 3 Gaussian, or with hidden Markov model. So here's kind of a proof. I'll skip it, just optional. It kind of shows you again that proof that we add here KL distance explicitly, and this is why we get the maximum ELBO when we take the previous distribution, the posterior, and we assign this our next model. This is really the E step, where we take for the current model the posterior distribution, and we kind of reassign the points to that new distribution and repeat the process. And you can kind of repeat the same logic and just show that there is a convergence. Graphically, we have seen that this kind of goes up and will be stuck in the local maximum. Couple more. It's a long lecture. I don't think I'll make a break. I'm gonna probably finish it, and we'll show the examples, the actual musical examples tomorrow. But here is just a visual representation of EM for the Gaussian mixture models, very much like what we've seen, but this is kind of shows this step by step. So you start with initial Gaussian distributions, and then it induces some sort of a probability over points, and these are more likely to belong here. Once you do this, so it's just exactly the same as in the KNN, just that everything here is kind of soft assigned, okay? And then you update your Qs, okay? And then, sorry, you update your Gaussian parameters, the data parameters, then you have the new reassignment of points, which will induce now other probability on the data points. You use this one to update your Gaussian parameters. This again induces a distribution over the data points in the posterior on the likelihood of these Gaussians, and then you use that and you can recalculate the model parameters, and then you end up in this setting. For PCA, you can also have a version which is a probabilistic version. I like this example because it's intuitive, but as any intuitive example, it also raises a lot of questions. So, you know, if people want to look deeper into that, just please ask questions on Piazza, or you know, when we're done, if we have time. So what is the expectation maximization version of principal component analysis? if you remember, we said that principal component analysis basically tries to find axis. It kind of tries to find the principal dimensions or axes for sort of a Gaussian that we fit to the data points. And the idea to do this in a probabilistic way is, well, you start with, so we look now, let's say we want to do dimensionality reduction to one dimension. So it means we want to find some line, single line, that will best approximate this data if we project it. So we start with some random line here, which is just initialization, and these are the projections, okay? Now, if you do these projections now, okay, basically what we have is, you can think now that these projections as strings that pull this rod. Okay, so if this is like a rod that you connect to all these points with springs, and you have you know, these connection points, it will now basically you can recalculate now the best orientation for this rod, and it will shift here. Okay, now by shifting here, these connections are basically sliding. These connections will slide to the new position. Okay, once they slide to the new position, okay, they will keep pulling this to the next position. We'll slide it again, and then they will eventually stop in a local kind of equilibrium point, where basically these strings don't exert any more. Or there is no good reason to kind of move this anywhere, because they kind of optimally balance each other. So this is kind of a physical analogy to going through the steps of expectations and maximization, where basically every time the rod shifts, you kind of maximize your model parameters, and then the expectations are by reassigning other points to the new model by shifting, you know, these projections. So if you think about this as, you have these little rings, right, that kind of can slide. So every time the rings move, this is basically your expectation step, and maximization is when the rod moves. So I think that's actually described here. Right? In each step, keep the rod fixed and allow the attachment points to slide up and down. And in the M step, you rotate the rod. Let's go back quickly to variational Latent Coder and kind of see where we stand on relating these concepts to each other. In the original ELBO, we wrote this in an early slide. We have this ability to write the likelihood of our model given the data as trial likelihood, or trial probability, and this joint probability averaged with the posterior. Okay, so just the language, just getting used to the language takes a while, right? So you average on the posterior distribution of the latent states given the trial distribution of these two parameters. So the important point to understand here is that we're trying just to solve the same problem of variational inference like we do in GMM or probabilistic PCA, but with a neural network. And like very much like in PCA, where we could find maybe some closed form solution to this issue, we want now to go and do this in iterative way. And this is where the neural network formalisms come in so strong. These are all basically differentiable programming. So we want actually to write this as a neural network problem by defining, again, let's repeat the basic principles of using neural networks, we need to create some architecture. We need to define the loss function, and then we need to take an optimizer. And the thing is that we hope that this optimizer can run a gradient descent or have some optimization method that will iteratively update our parameters of the network until it finds a local optima of the loss function, right? So thinking about this in these terms, I think kind of clears things out. I mean, this is really what these things do numerically. Now, this is our loss function, right? So we kind of almost did everything here, right? We designed some neural network Q, and we designed some neural network P. And so we specify the parameters. This will be the weights of these neural networks. We'll see them in a second. We write this loss function, and we'll see more explicitly what they are in a second. But can we plug this into into auto differentiator or into some kind of an optimizer that will be able now to move towards a better solution, right? So in EM, there was a way to do this with these E and M steps, but here we actually need to differentiate this function. So if we want to differentiate this function, there is this jumping notation here, so pardon me for that. So let's say we want to optimize on some parameters theta, even though these are the same theta, but the F and Z is kind of just written in a very general way. So you can think about us trying to do an expectation over some function, but Z is now random parameters, okay? So if you think about this, this is kind of an integral here. So we have the derivative and we have an integral of FZPZ. So if we want to now throw in the differentiation inside the integral, we have to observe the chain rule, which means we need to differentiate over F of Z, and then we also need to differentiate to make some derivative over P of Z, but P is probability. Okay, so we have difficulty of doing this, and this is where the idea of the reparameterization comes in. If we can rewrite P of theta Z as some other function G of theta that is parameterized, and we have a noise E that kind of translates this function, we can actually just do the math here. We can put the the gradient inside, and then we can basically approximate this by averaging, by sampling this epsilon. This is really what this whole process of frame normalization does. It tries to solve an issue of backpropagation, or the expectation that has to be differentiated if we want to actually run this differentiator on this expression. But we need to write this as deterministic expressions and write it in that closed form analytic solution. So what the VAE, the original paper, it's a little bit hard to read this, but there's some other tutorials that Kingma wrote. Basically what he does, he proposes an analytic solution for the KL losses. So if you remember, we kind of subdivide this into two losses. We have the next slide to show this, but kind of just, I put here the equation. He can actually, by assuming this ring organization trick, he can actually write one aspect of this loss function as analytic expression in sigma and mu, and now you can estimate these using neural networks. So here's actually what we have, and this was super dense and quick introduction to all of these concepts, but bear with me for a few more minutes. It's really actually having such a long set of slides without a break is hard. Okay, in the future, maybe I need to break this into subsections. This is our ELBO, okay, and this is where the reparameterization tricks comes in, and it's done for differentiability. So again, we need to have a loss function, and what it does, this rewriting is splitting the loss function into these two things. You have the KL aspect here, and you have this one, which basically can be now computed using mean square error. Need kind of to explain and see why this is a mean square error, but basically what we do is we have the X, okay, which is our data. It's encoded by estimating two things, the means and the variances, the mu and the sigma. So you have two neural networks here that basically take the data, and then they induce a probability distribution. How they do that? Well, now you think about one as variance and one as mean, and every time you sample now from your Gaussian, okay, which is this, you can generate a latent variable z, okay. So you'll be learning sigma and mu as neural networks, as deterministic functions, and we'll be just sampling from this epsilon. Now, once we have that, we have a decoder here, okay? This is another neural network. So we have basically 1, 2, 3, 4 neural networks here, but this neural network now will generate an X, okay? And this X is basically emulating the posterior distribution. Basically, given Z, we try to learn some decoding function, and we generate X reconstructed. And we need to have some other measure now, as in normal autoencoder, right? In normal autoencoder, we had a mean square error between X and X reconstructed, right? Here it's still written as log of P, but if you do the math and put here some assumption in Gaussian distribution, you can actually show that this becomes mean square error. But basically, this is kind of the more abstract way to write this. So we can calculate now this error in the reconstruction, okay? And this is really what it does. We sample these Z's. So this is why it's mean, because you sample a lot of these Z's to accomplish the E. And the square error is this, okay? So this part is actually responsible for trying to find a decoder that kind of works best. But again, the Z's are provided to that decoder. So we can also influence something about the encoder, right? So we need to backpropagate here, but there's something also about reaching to these points. So we have this additional loss function, KL, okay, which is this variational loss, okay? And so what a variational autoencoder has is this combined loss, the reconstruction loss, and the variational loss. And the variational loss is really this part that will push this approximate distribution, the trial distribution, to be such that it will push the ELBO to its boundary, basically to try to maximize the lower bound by this computational loss. So again, in the previous slide, oops, it should be the previous slide, this was written explicitly through the parameterization trick. So this is computed analytically. So basically we can now backpropagate everything and run these iterations using TensorFlows and or Keras, okay, using one of the optimization frameworks. So again, the framework itself, these neural network frameworks, they're not probabilistic. I mean, you can sample, of course, you can have probability distributions there, and we'll be sampling from Z's to generate this part. But once you think about the optimization process, it's done deterministically. You can say, well, there's this concept of gradient descent. You can say there is stochastic gradient descent by basically sampling from your data. But the descent itself, the gradient descent, is deterministic. So this is what we have in the variational autoencoder. And at least kind of I hope that with putting everything together and summarizing everything in one perspective, please try to go through these slides maybe a couple of times just to see if kind of that flow of logic of why we want to move into latent space and why we want to have that latent space or graphical model with these hidden variables, why we want to treat them as probabilities, and this is why we kind of use the Bayesian formulas there, and then it becomes encoding, decoding as probabilistic posterior functions, and then in the variational autoencoding setting, we can rewrite everything so we can use the optimization tools. While in other settings, you can use the same loss function, the same concept, and come up with other algorithms that eventually kind of fulfill the same logic. And the logic is really to find a probability distribution over our data so that the data will be most likely, okay, or have the highest probability of being generated using this model. And this is really where the generative part starts, is that we assume that there is a probability distribution or an information source that generates our data, and we are searching for the right model or the right probability distribution in some family of possible distributions. And in a variational case, we take another family of distributions, which are trial distributions or approximate distributions, that we can do something with them, we can calculate, we can do some math, and we have ways to approximate. We do our search by adjusting things that, so we kind of look under the lamp, but we move the lamp. So that actually kind of makes sense, right? So we're looking for something, we don't know exactly what's happening, but we can kind of slowly, using a distribution that we know how to handle, change its parameters until we get to a point where we think, at least locally, we capture a good description of the data, because the data itself was governed by a different distribution that we don't know. Okay, if we can hold for another moment, take a deep breath. Just one more slide, trying to relate this to another concept that we introduced, and the idea of also connecting concepts. I think this is something that kind of drives my logic of building, the lectures. It's really that you can later go back and kind of put the pieces together. So from this, I don't know how many feet above view of machine learning with all the models, I want to mention also something that we mentioned last time, and that was when we introduced neural networks. We spoke also about the issue that depending on the data, we might deal with categorical data rather than with numerical data. And this is really relevant for music, because you need to decide how you treat your notes. We have seen already the idea that backpropagation cannot be performed through stochastic nodes, and that's the reparameterization trick. Now, you can think also about the problem that your features, okay, or your data is described as categorical features, such as multinomials or some other discrete distributions. So that also creates a problem for differentiation, because you cannot perturb, it's impossible to do perturbations on the parameters of a discrete distribution. So there is this other concept that I'll just throw in. So if you've heard this or encountered this, it wouldn't be totally new to you. And it's called Gumbel distribution. And this is kind of a way to combine the softmax with variational autoencoder. And it allows us basically to take a one-hot representation and plug in here the softmax, okay? So you have here another option, or not another option, it's kind of a little bit more complicated way of trying to use variational autoencoders with categorical variables. I will leave this at this point. We might return back to talk about Gumbel distribution if this is relevant to some of the projects or if time permits. But I think this is pretty much where I end my presentation, and I'll move to questions.